You're here because you want to master Redox with a University of Cambridge graduate. Let's begin. Hi, I'm Brendan, and I've been helping students like you achieve their mastery over chemistry over the past 8 years, and I hope that you can learn something from me today. Before we begin, be sure to go into the link below so that you can download a free copy of my notes and use it to follow through our lesson today. First, we have to understand what is a redox reaction. A redox reaction, is a chemical reaction, right, where one substance undergoes reduction and another substance undergoes oxidation. And usually in our syllabus itself, we know that both oxidation and reduction usually occur together, right? And this is the definition of a redox reaction. So when we are answering questions that ask, how do you know this is a redox reaction? You have to explain, this is this reduced, this is this oxidized, and since oxidation and reduction take place in the same reaction, it is a redox reaction. You need to know when oxidation happens. This happens when there is a gain of oxygen in a substance, loss of hydrogen, loss of electrons, but the biggest one is that there is an increase in oxidation state. An increase in oxidation state is the biggest telltale that there's an oxidation reaction happening. It is the biggest, because sometimes you could have a gain of oxygen but there is just no oxidation, for example. Or sometimes you can lose hydrogen but it's not an oxidation reaction. It's kind of weird, right? So you often want to look at the oxidation state. Reduction is the opposite of oxidation, so you expect the opposite, right? It will happen when there's a loss of oxygen, or there's a gain of hydrogen, or there's a gain of electrons, or there is the biggest telltale, the decrease in oxidation state. So how do I calculate my oxidation state? I actually got these rules from Genie Teach, right? I feel like these rules are very good. So some general rules for oxidation state, which is an important skill you need to have when you are tackling redox questions. So it follows these few sets of rules. So rule number one, your neutral elements, like a hydrogen gas, your sodium, magnesium solid, your oxygen gas, these always have an oxidation state of 0. Number two, your ions with fixed charges, your group 1, group 2, group 7 ions and aluminium, these all have a fixed charge. So your sodium plus, your calcium 2 plus, your bromine, these all have exact oxidation state, which is the same as the charge that they have. So for sodium plus, since it's a 1 plus charge, it has a +1 oxidation state. Hydrogen in a compound tends to be +1 as well. So your HCl, your H2O, your NH3, your KOH, except for these exceptions that I will cover on later. Then rule number 4, is your oxygen in a compound. This tends to be a -2 oxidation state as well. So your magnesium oxide, your sodium oxide, these tend to be -2. Except for an exception that I'll cover later on as well. And then rule number 5, the sum of your oxidation states, is to be the same as the charge on the anion or cation. So this typically applies, to our complex ions, For example, you have multiple elements, in the same cation or anion, For example, sulfate anion, carbonate anion, ammonium cation, These, when you total up all the oxidation states, you need to equal to the charge, the overall charge of the cation or anion. And I'll go through some examples later on. So we know the hydrogen oxidation state tends to be a +1, except for these few cases. For example, in a metal hydride, we know that our magnesium, for example, has a fixed charge, so it's a +2 oxidation state. So total is a +2 from magnesium, To make it overall neutral, you know that the overall from the hydrogen needs to be a -2, And since there's 2 hydrogens, each hydrogen is actually a -1 over here. Understand? So this is how we determine our oxidation state for these exceptional cases. So hydrogen is -1. Very interesting over here, when it's usually a +1, means the hydrogen is actually gaining electrons. Another interesting case is hydrogen peroxide, H2O2. So you would generally think that oxygen, each have a -2 oxidation state, and oxygen in total will have, since there's 2 oxygens, it will be a -4 total from here. So it should be a +4 total from the hydrogens, to make it neutral. So each hydrogen is a +2. So this is a very common way to think about it as an exception. Actually, this is the wrong way of thinking. Actually for hydrogen peroxide, this hydrogen over here actually has a +1 oxidation state. And this is the way we have to think about it for hydrogen peroxide. So if it's not really an exception for hydrogen, then it must be an exception for oxygen, and you're correct on that. Okay, so if you look up over here, the exception in oxygen is that each hydrogen, right, is a +1. So the total hydrogen oxidation state is +2 since there's 2 hydrogens. And then because it's overall neutral, the total oxidation state from O2 has to be -2 to keep the whole thing neutral, right? So each oxygen is actually a -1 oxidation state. Okay, so this is a case where the oxidation state of O, right, is actually -1 instead of -2. So what are some examples of how we calculate our oxidation state? I've kind of roughly showed you the method, right? But in general, you want to follow those basic rules that we said just now. For example, for SO42 minus, right, a very complicated one, we know that each oxygen is a -2. Okay, so if there's 4 oxygens total, there is oxidation of -8 oxidation state, the sum of it. To make the whole thing overall a charge of 2 minus, this S has to in total have +6 oxidation state. So the oxidation state of S is +6. Okay, to overall make this whole thing a -2 charge. Let's look at SO2 for example. SO2, right, the oxidation state of O is -2, right? We know this from the rule. So in total, since there's 2 oxygens, it will be a total of -4 from the O's. So to make the whole thing neutral, the total oxidation state of sulfur has to be a +4. So the oxidation state of sulfur is +4 since there's only 1 sulfur. Okay, you can see how the oxidation state can change for sulfur, which is why you have to usually calculate this from scratch. Okay, lastly is KMnO4. Right, for KMnO4, you have to realize that this is an ionic compound. Right, it's composed of K plus and MnO4 minus. Right, so the oxidation state of K is +1. Okay, and then from MnO4 minus, right, each oxygen is a -2. With 4 oxygens, that is -8 in total. The overall charge of the MnO4 minus anion is a -1 charge. So to keep the whole thing a -1 charge, right, you need to give a +7 to the Mn, the manganese ion. So the total oxidation state is actually a +7 for Mn. So this is how we calculate the oxidation state for each and every element inside. Hope this is clear. Alright, so once we are able to calculate our oxidation states, right, it will make this thing very easy later on, right? We can then figure out, right, if there's an increase or decrease in oxidation state, and hence determine if there's oxidation or reduction for a particular chemical substance. Once we know that, right, okay, we can now talk about oxidizing agents. Oxidizing agents, right, is a reagent, right, that causes another substance to be oxidized. But a very important concept is, if you are an oxidizing agent, you yourself will go through reduction. Okay, because when you oxidize someone else, you yourself will be reduced. Okay, you must know this concept very well. Okay, when you know this, right, you can easily identify an oxidizing agent or even a reducing agent. Okay, so an example of oxidizing agent you have to know is acidified potassium manganate 7, aka KMnO4. Right, this is a very strong oxidizing agent, right, and it will undergo reduction in this reaction. Okay, and this is actually the reaction that happens over here. Okay, you'll realize that the oxidation state of manganese, right, decreases from +7 as we calculated just now, right, to a +2. Okay, so it itself got reduced. Okay, and the color of the solution will turn from purple to colors. This is an important observation. How do I memorize this observation? Okay, you can memorize it as MPC, which is manganate, okay, purple to colorless. Okay, you can also memorize the acronym MPC, okay, as my pet cat. Okay, so just remember about your cat. Okay, and then you can determine the color change as well. Okay, then we can talk about our reducing agents. Okay, reducing agents are the opposite, so they cause another substance to be reduced. So they themselves will be the opposite, they will be oxidized. Okay, they will undergo oxidation. For example, potassium iodide. This is one that we have to remember. So it's a common reducing agent, okay, and it will undergo oxidation. So this is the reaction. You'll realize that it goes from -1, okay, because it's an I- ion, okay, to I2, so it's a pure element, so this is a 0 oxidation state. Okay, and because it actually increased from -1 to 0, okay, it itself went through oxidation. Okay, and you must memorize the observation over here. This one, the color of the solution will turn from colors to brown. You must memorize this. Okay, it's brown because I2 itself is generally a brown solid. If you enjoyed today's video, do remember to click the subscribe button so that you can enjoy more free content from us and improve your chemistry with us together. If you want to join my community of students to learn more secret formulas to acing chemistry, do check us out in the link below and sign up for a free trial class today.